PowerBoost also has effects on the latency that users perceive, as well as the loss rate. Here we've shown PowerBoost latency effects for two different users. The latency is shown in terms of round-trip time in milliseconds, and the loss rates are shown on the right side of the y-axis. Latencies are also shown in a log scale. In this particular experiment, we start sending traffic here and we stop sending traffic here in both cases. We can see that even though PowerBoost allows users to send at a higher traffic rate, actually users may experience high latency and loss over the duration that they're sending at a higher rate. The reason for this is that the access link may not be able to support the higher rate. So if a sender can only send at R sustained for an extended period of time but is allowed to burst at a rate R for some shorter period of time, then buffers may fill up, and the resulting buffers may introduce additional delays in the network, since packets are being buffered up rather than dropped. TCP senders can continue to send at higher rates, such as little r, without seeing any packet loss, even though the access link may not be able to send at that higher rate. As a result, packets buffer up and users see higher latency over the course of the PowerBoost interval. To solve this problem, you might imagine instead that a sender might shape its rate never to exceed the sustained rate big R. If it did this, then it could avoid seeing these latency effects. So certain senders who are more interested in keeping latency under control than they are in sending at bursty volumes may wish to run a traffic shaper in front of a PowerBoost-enabled link. So shaping traffic to a rate of less than this sustained rate R can prevent this buffering. More details about PowerBoost and the experiments that we've run to keep latency under control in its presence are available in a paper we wrote called Broadband Internet Performance: A View from the Gateway, which appeared in SIGCOMM 2011.